Good morning, everyone, and welcome to this concept webinar. Today, we are going to talk about Introduction to Computational Fluid Dynamics, and we're going to see how it can be used to boost design. First, few words about concept. Our mission is to help innovative small, medium enterprises and freelancers to improve engineering design of their products. We are going to do that providing design software easy to use and accessible everywhere. Our business is CFD on cloud. This is our main product, but together with it, we offer also consulting activities both on development and also optimization of your products, support with qualified technical personnel, events like these webinars, and also training on-site and remote served. At the end of the presentation, you will see how this product is organized, and after that, you will see a real-time application of it. But now, let's focus on this course of Introduction in Computational Fluid Dynamics. We are gonna see few fundamental concepts about CFD, and we will start with examples of fluid in motion. In fact, fluid dynamics basically is the study of the fluid in motion. You can find examples in everyday life, like meteorological phenomena, like human physiology, industrial equipment, or object and fluid interaction. Take as an example vehicles, planes, and ships interacting with air or water. Every one of these settings involves a fluid in motion. The motion of the fluid can be studied in many different ways. We can see here that there are at least three fundamental ways. The first one is the experimental one. It's the experimental fluid dynamics that basically consists in real tests performed on facility tests like wind tunnel, for example. The theoretical fluid dynamics is the study carried out on the equation described the fluid in motion. These are carried out through mathematical elaboration of the equation. Instead, the computational fluid dynamics is the same analysis on the same equation, but carried out through the use of computers, and so iterative models and solution of this equation, usually with the aid of submodels to simplify the complex equation behind it. So, what is CFD? CFD is the acronym that indicates computational fluid dynamics. It has been diffused since the 80s as an industrial application, and now it is widely used in order to design and perform engineering optimization. The goals of CFD are basically those of studying the fluid motion to obtain qualitative and quantitative results of interesting quantities. Let's say, as an example, can be reported velocity, contours, or pressure, or temperature in your study. So through this instrument, it is possible to perform numerical experiments in a virtual laboratory. Many instruments used by CFD are mathematical modeling, since the user has to choose the right set of differential equations that describe the phenomena. Numerical modeling, by means of which these equations are discretized on the domain and they can be solved through numerical schemes and techniques. The user interface at the end is the instrument that allows the user to interact with a whole system, offering a simple way to deal with this matter. Why to use CFD? Usually, it can be applied in a very wide sector of engineering fields. For example, an architect or an engineer can use CFD to optimize the design of a building, or a designer can optimize the external shape of a vehicle in order to minimize the aerodynamic drag. Again, a biomedical engineer can improve the design of a prosthesis in order to improve the rate of success in blood vessels implants. So, as you can see here, there are a lot of applications for CFD. Today, we are going to see one specific application, and you will learn how it can be used to improve and optimize design. Someone may ask, why to use simulation when we have experiments? Well, there are a lot of advantages in using simulation. Let's take as an example the quantity of parameters you can analyze through it with respect to those allowed by experiments, the spatial and time resolution, or the test scale available. You cannot put an entire airplane inside a wind tunnel. Instead, with simulation, you can perform real-scale tests on it. The economic advantage, or also the typology of the studies you can realize. Let's say, with simulation, you can easily simulate an explosion, something you cannot do with real experiments usually. So, it's clear that simulation has a lot of advantages, but of course, there are also some limitations of this instrument. The CFD results can be highly dependent, their accuracy can be highly dependent on a number of factors. Let's say physical models. Physical models are something that can really lower your accuracy if you not select them appropriately. Numerical methods, every time you have to solve equations through the use of a computer, you have to consider the errors dependent on the machine precision and also the accuracy of your algorithm. Finally, boundary condition. Basically, it's the accuracy that you use when assigning values in the limit of your boundary. Let's say you have to simulate the inflow inside a parking lot, and you have to assign the profile of the entering air. If you don't do it properly, this inaccuracy can reflect in poor solution. So let's now see how a CFD simulation works. There are 5 steps. You can see them here. The first one is the geometry step, then there is the grid generation, boundary condition assignment, solution of the equation, and finally, you have to analyze your results. Geometry selection is something that links the problem with the geometry. Usually, you have to start using a model of your geometry that is usually a CAD file. Typical formats are, you can see here are STEP, IGES, and STL, and they have to adhere some requirements. In particular, they have to represent the fluid domain. That is basically what is the part of your geometry that is wet by your fluid. Let's say, as an example, a vehicle inside a wind tunnel. The fluid domain is constituted by the wind tunnel itself, except the internal part of your vehicle, so that, let's say, seats or the steering wheel are not meaningful features of your geometry. At the same time, your CAD has to reflect how it is going to be built in the future. So, as an example, cast or compenetration, material compenetration, has not to be present in your CAD model. Grid generation is the step when you subdivide your entire fluid domain in small pieces, in small sub-elements. This complex is called the mesh. The mesh is constituted of these sub-elements and has mainly two important features. One is the typology of the elements you are using, and some examples are represented in this slide. And the other one is the refinement, the so-called refinement. That basically is a factor that tells you how many elements you are going to have in your domain and how precisely you are going to discretize your problem. In fact, the more elements you have, usually the better accuracy you can obtain. And now, talking about boundary conditions, when you have to simulate a specific problem, what makes it different respect to other problems is that you have to assign your particular condition. For example, the wind flow velocity or the pressure of your pump. Or in this way, you are differentiating your problem with respect to the general one. You have to follow some rules when assigning the boundary condition. In particular, you have to be particularly accurate in order to obtain an accurate solution. And also, you have to be sure that your boundary conditions are consistent. In fact, let's say you have to simulate a wind flow through your wind tunnel. If on the inlet you assign a velocity that is going inside your domain, on the outlet you have to define a consistent boundary. It means that if you assign an inlet also on the outlet, let's say a velocity entering your fluid domain, the air cannot exit in any way, so it would be a problem leading to error or an inaccurate solution. About equation solution, well, once you have defined your boundary condition and your domain, the equation describing your model will be written in a linear system that will be solved through the aid of numerical iterative methods. Usually, there are two questions that are important at this step, and the first one is, how many iterations do I need in order to consider the system solved? It strictly depends on how you measure how far are you from verifying the conservation law that constitutes this equation. Usually, those that are called residuals are used in order to identify how far are you from the correct solution. What influences the result accuracy? It depends on many factors. The most important one are modelization accuracy and appropriate resolution, and in general, the problem setup. Finally, let's go to result analysis. And this is the step when after the simulation is complete, you look at the general flow configuration and you are looking for insights in your study in order to understand how well your product is designed and where it can be improved. There are two kinds of tools usually employed in this process. Graphical tools like contour plots, vector plots, streamlines, or numerical tools like flux balances, volume and surface integrals. Let's say as an example, if you have an airplane or a wing, you may be interested in evaluating which forces like lift and drag it can develop, or on which moments act on your body. So this is the CFD simulation, how it is organized usually. And now let's see how our product implements this concept. What do we mean with CFD? If you imagine a traditional wind tunnel, you can put it inside a workstation. What you think is a virtual wind tunnel. This is the CFD. Well, we perform a step further. We put the virtual wind tunnel on the cloud. As I said before, there are a lot of applications in CFD, from turbo machinery to engines. You can find CFD application basically in every industrial sector. Here, we are gonna recall the steps of the CFD simulation. As we already seen, there is a creation of the CAD model. The step, usually, right at the moment, we have step files, IGES files, and STLs. There is the definition of the geometrical grid. Then we have the definition of the CFD setup, and finally the results analysis. Let's deep in console features to understand a little bit more how our web-based CFD is implemented. As I just said, CAD interface is allowed to upload files in STEP, IGES, and STL formats. Different Unity systems like the international one and the imperial one. We also have the possibility to automatically create the wind tunnel for external flow. Talking about meshing, we provide two different meshing algorithms, the hexahedral one and the tetrahedral one. In addition, you can also perform the boundary layer for wall refinement, and the procedure is guided since it's divided in two steps, the surface mesh and then the volume one. Talking about CFD, we have a lot of different configuration available. Multiple flow models are available, from incompressible flow to ideal gas. There are a set of most common turbulence models. We can perform laminar and unit simulation, or kappa epsilon, kappa omega, and Spallard Almaraz turbulence models. Finally, you can perform both steady and transient simulation. One thing that I would like to underline here is that since our core technology is based on OpenFOAM, you can rely on certified and validated results. Proceeding, we can see the analysis that you can perform with ParaView on web. That is a widely used tool in the scientific and industrial world. You can directly online, you can complete different analysis like extraction of light, streamlines, profiles, and contour. You can also download screenshots of your simulations. Apart from that, we offer even more features. There is a complete support available online. There are test cases and tutorials you can find at wiki.concept.com. Hardware resources are basically unlimited and available 24/7. Finally, we can provide dedicated software development in case you have specific and custom needs. Let's take a look at what's next. We have release 2.0 planned for March 2016. We will provide specific application for HVAC and fire simulation, external flow, turbo machinery, and oil and gas like valves and tanks. Finally, let's take a look at our pricing table. We offer at the moment different plans for freelancers or for enterprises. We have 2 subscriptions one that is usually monthly billed and the other one that is annually billed. If you want, you can start for free. There is a 14 days free trial. You can register at concept.com and start using it right now. Just enter your details, your personal details. Let's now take a look at the application. I will let you with Ruggero, that is my colleague, and he is going to show us the complete setup of our CFD simulation online.
Thanks, Alessandro. I am Ruggero. I am one of the Concept founder and expert in CFD simulation. And I'm going to guide you through a very easy to do tutorial, let's say, that shall overview the functionalities we saw in the presentation of Concept CFD web-based solution. Well, as you can see, I am on a browser. I typed the Concept website, www.concept.com, and I'm gonna now log in our application. In order to do that, just type login, and you'll be forwarded towards the application. In here, you can insert your personal details, and in case you can also register, in case you haven't done already. It is also possible to register through some of the most popular socials. For the present simulation, I'm going to use a Concept account. It is obviously possible to buy Concept credits. You just have to go to your account and go to the shop. All right, so store, buy. But having a look at the simulation, having a look at the configuration of our dashboard, well, we have a quick overview of the situation of what we are spending with Concept. This big disk we can see over here, it's the credits available that are used to run the simulations. We are going to see later the other graphs as we can understand them better after the tutorial, but it's very important to note that both the user manual and the support are available just by clicking one button. I wanted to go with you to the manual, which obviously describes all the features and all the configurations available with Concept. And in the current tutorial, we are gonna redo one of the tutorial available in our wiki. Just click on CFD application on the left and HVAC. The case we are gonna see is the car park simulation. It's a very simple case in which we have this car park. You can see over here, you can see all the car boxes where one can leave his car. And this car park has a window on the ceiling, this one, and one ramp to access the car park. Okay, so the flow in general goes from the window to the door. In order to make the flow flowing, sorry about the joke, we installed a fan. This is many times also a fire prevention situation, in which with this fire, we are able to evacuate the smoke and the heat produced by the fire in a quicker way than using only natural convection. So in the simulation, in the test case, we're gonna analyze quickly the flow inside this car park induced by this fan. So we just need to get the file, which is right here. It's a step file. It's one of the files accepted by our CFD application. And with that file, we can actually create the case. We're going to see how to do that. Well, obviously, the first thing we have to do is to type in a case name. It's going to be webinar 5 November 15. And I type create. Automatically, I am forwarded to another screen in which obviously I'm asked to upload the file. I select the file I previously downloaded. 1 second. And as you can see, the file is automatically uploaded to our system. The next selections I have to do is the file units. This refers to the possibility to modify the files from international system unity measurements to another one, imperial. For this particular case, the file units are centimeters. And then there is another very important parameters. We defined in the geometry file I uploaded the several boundaries by applying them different colors. You can see yellow for the top window, this kind of pink for the access ramp, and then there is blue and orange for the fan push zone and suction zone. So I select the fine boundary by curve color. In this way, we are going to get the step file divided accordingly to the color I did that previously. So we move to the next section and we get into the domain, in which we can select whether the flow is internal or external. Obviously, if it is an external flow, we are asked to insert the bounding box sizes. For the present case, it's just a normal internal flow. Now that we have selected all these options, we can submit the simulation. We are asked to confirm the submission, and here you are. Automatically, the simulation goes in background and it is executed. Obviously, we don't have time in this tutorial to actually go step by step in all the details of the simulation. So let's have a look to what we have done earlier. This webinar HVAC is exactly the same case we have already run for you, and we can use now just to visualize the results. As you can see, I am now in the mesh 2D phase. So after I have uploaded the geometry file in the geometry section, I can now visualize the geometry. Here it is. All right. This is exactly the file, the same geometry we saw in the manual, in the tutorial. What's interesting over here is that we can actually see how the geometry has been divided. Like we can highlight the red zone, if I can remember what the red zone is. Oh, here it is. It's the ramp inlet. I know that in this zone, I have to apply an inlet. And in this particular case, I can define the parameters that are used in order to create the surface mesh of this inlet. 70 and a max element size of 0.01, they are fine with the present configuration. Doing exactly the same for all the boundaries and submitting the case. As you can see over here, I have the submit button. It is possible to launch the mesh 2D phase. We're going to skip the launch and we are going to simulate. I have already done that. And we can now obviously visualize what we did previously by launching the mesh 2D, its results. 1 second. Here it is. What's the difference compared to the previous step? Now we can visualize the surface mesh. I just have to select the visualization to be surface with edges. Click apply. Here it is. This is the surface meshing as defined by the code. By keeping zooming in, as you can see, I'm now inside the car park. What we can notice now is that inside the car park, there is no volume mesh. This is because for the moment, we just meshed the external surface. And this is why we are now in the mesh 3D phase. In this phase, we have to select whether we want an hexahedral or tetrahedral meshing algorithm. And once again, the characteristic size of the elements in the volume mesh, so inside the car park, no more on the surface of the car park. We can accept the default settings, and in here, we are defining the boundary treatment. What do we mean? It's the boundary layer, so the wall refinement that is necessary in order to resolve the velocity gradient at the wall. We just leave the default options for this tutorial and we submit the case once again. Just pretend we have done the submission. We can go to the CFD step. This is the most important step regarding the final results. In this step, we are going to select how we're going to define the fluid models, the fluid turbulence, and some boundary conditions and some simulations parameters. Just as a preview, we can visualize the internal mesh. How we can do that? Well, once again, we select the geometry, and this time we click on this plus icon, and we create a slice, an internal slice. It's a cut. We're going to cut the mesh domain. We just leave the default parameters and press apply. Here it is. This is the internal slice of the domain. And what happens if now we turn on the representation surface with edges? Well, obviously, we can see what's inside. We can see the meshing elements inside of the domain. On top, on the right, and on the left, and at the bottom, we have a higher resolution because we define that in the mesh 2D phase. And inside of the domain, we have a lower resolution as we defined in the mesh 3D phase. So now that we are happy with the mesh, we can choose the algorithm, the models, the CFD models. So as specified earlier, it's possible to choose incompressible or compressible flows, and there are many turbulence models available. We just select a Spallard-Talmaras. Here we have to define the flow properties, such as density, such as pressure and velocities as initialization, dynamic viscosity, and Spallard-Talmaras variable viscosity. When we move to the next section, we have boundary condition application, in which we are asked to specify pressure and velocities at all the boundaries. Okay, so the yellow boundary, red, navy blue, green, and gold ones. All right, so for each of them, it's possible to specify whether it's a gradient and value, and specify the value of the gradient or the fixed value imposed at the boundary. And in the last section, we can define whether the simulation is transient, so we have a time evolution, or we want just a steady simulation. So we just want to know the final results of a steady simulation. And obviously, we define the number of iterations and the output frequency, the frequency in which we want to plot the results. Once again, we skip the submit phase, in which we would have to wait a few hours in order to get the results, and we move directly to the results. This is probably the most interesting part of any CFD simulation, because in here we actually analyze what happened during the simulation. It is a little bit like after having performed a wind tunnel test, and we have now a huge number of data, and with this data we want to analyze and to see whether we are happy with the ventilation inside of the car park for this particular case. Well, let's move first of all to the last saved time step. And well, let's start a little bit with, once again, with the slice. We want to know what happened inside of the domain. So we click on the plus icon, we select slice, and we want to visualize the velocity. So we select color U velocity, color according to the velocity, and we select the slice to be Y normal. So we select the normal to be 1 in Y direction, and we select a Y coordinate of 50. We press apply, and this is the velocity. As you can see, we have this light blue value over here. It's because we haven't defined the correct range of values for the legend. So we have just to turn on the legend. Here it is, the legend, with the range of values, and we made the legend range smaller. So we just select the maximum value to be 0.3. We apply, and here it is. Now we have a much nicer visualization on the flow results. But we are still not happy. I want to see where this slice is compared to the car park geometry. So how can I do that? Well, let's just put the car park with some transparency. So we just go down and we scroll down to representation, and we define the opacity to be 0.1. By selecting apply, here it is. Now we have a clear overview of the location of the slice compared to the car park. We are exactly at the center of the car lane. Oh, we are very happy because it seems that the flow is actually moving quite a lot inside the car park. In order to move our analysis, our results analysis even further, we want to plot the stream tracer, so the streamlines of the flow from the top ceiling window to the front ramp. What we can do, once again, we select system.form, the plus icon. We move this time to the stream tracer. This is a tool that allows us to plot the streamlines. All right, we select color according to the velocity. We select in sources vectors to be calculated from the velocity. And we select a point source to be located at Y coordinate equals to 50. When we choose apply, here it is. Here they are, the stream flow. As you may notice, the system automatically re-updates the velocity range. So I have to move back to 0.3. I click accept and I turn on the car park, and here it is. Now I have a complete visualization of what's happening inside of the car park, and I can see these two vortices induced by the fan, by the application of a fan at this point. Now, in order to download the picture, we just have to click on this Save button. We define the screenshot resolution, and we click on Capture. Here it is, the screen. So we can right-click on it and save it on our local machine. With this, I finished my tutorial. So now we can move to the question, if you have any. Just as a reminder, in order to make us question, just go on the top right, there is an icon composed of several small squares. If you click on it, you can access the question and answer Q and A section, and by clicking on it and typing your question, you can interact with us. So I invite Alessandro to join me, and it's time now to reply the questions. Okay, we have one question. Alessandro, if you want to answer that.
Yes. Well, the question is, what browsers are necessary to use the platform? Well, most common browsers and most diffused ones are guaranteed to work with our platform. So I'm talking about Google Chrome, Mozilla Firefox, and Internet Explorer and Safari. Talking about operating systems, you can use Linux, Windows, Mac OS X, but also Android. So the most important thing that is that you have to make sure you have installed the last version of the browser, and you have to be sure also that you have a nice internet connection.
All right, there are some more questions. One more question is, what local resources are necessary to use the platform? Well, the simulation and everything is performed on Concept servers, okay? So the hardware requirements are highly limited compared to standard CFD software. You just need a laptop, and probably you can run the simulation also by using a tablet. Having said that, you need to have a CAD on your local machine in order to produce the 3D model that is used to perform the to create the 3D model that is used to perform the simulation. Sorry.
Okay, so then we have a question about subscriptions. Well, as we told earlier, we have different subscription for freelancers and for enterprise. We are currently offering 4 different subscriptions plans, and they are different in terms of number of credits you will gain and also the expiration date of these credits. There are 2 monthly billed subscriptions and 2 annually billed subscriptions. In the very same time you complete your purchase on our shop, the credits will be added to your account and you will be able to use the platform right away. The expiration date is depends on which kind of subscription you buy, and if you need more credits, you can just write us or purchase another subscription plan.
Let's wait if there are some more questions. Yeah. What happens if I don't have internet? Does my simulation continue running? The answer is simply yes. Once the simulation has been launched and once it goes in background, let's say, the simulation keeps running regardless we are connected or we have turned off the computer. All right, so we can log out, move somewhere else, and we can come back. Automatically, the system gives you an ETA, estimated times of arrival. So it tries to tell you how long does it take that particular simulation to finish. It's obviously estimated. It may vary a little bit. But with this system, you know in advance how long it will take. And so you know for how long you can log off and do something else.
There is one more question about the access, how can more people access from the same account? Well, the account is a personal one, is linked to one and only user, but different users can use the same account credential to access the platform, and so share the same simulation dashboard and the same cases. If in the future this feature will be requested, it is possible that we will implement a team function in order to allow a group of users to collaborate through the platform.
All right. If there are no more questions, we can, I think, Alessandro, consider this session like over.
Okay.
And thus, we invite everyone to visit our website, www.concept.com. We also invite everyone to check out all the other events we are organizing. Just go to the event page or to the address consult.com/events, and you can register to all the other webinars, we are organizing. So thanks, Alessandro, for speaking. Thanks in particular to all the attenders and viewers of this webinar. And see you to the next one. Bye.
Bye-bye.
Bye.